Okay, I'm going to do number 7 on its own video because I think it's probably going to take us the full 10 minutes. So we're on page 640, and number 7 says 3 charged objects are located on the vertices of a right triangle. Charge A, which is 5 microcoulombs, has Cartesian coordinates of 0, 4. Okay, so 0 is the x direction, 4 is the y direction. Okay, and if you keep reading, it says the coordinates are in meters, so really what they're telling us is this is 4 meters. It says charge B, which is negative 5 microcoulombs, is at the origin, and charge C, positive 4 microcoulombs, has coordinates 5, 0. So x is 5, so this is 5 meters. And then you could find this. So square them, add them together, root, and take the square root. So this will be root 41 meters. Okay? And now the question is something I would never actually do to you. Oh, by the way, I'm leaving it as root 41 because we're finding force. FQ equals KQQ over R squared. So we're just going to end up squaring this root 41. So I figured there's no sense taking the square root, rounding it, and squaring it, and not get 41 back. The question wants to know the net force on each of these. Now, if I were to ask you this for real and anything other than a practice question, I would only ask you the net force on one. But since there's only one like this one's a good practice one. So the first step is to find the force that A is putting on B, B on A, the force A is putting on C, C on A, and then the force B is putting on C. So treat each pair and do FQ equals KQQ over R squared for each pair. Okay, so FQ will equal KQA QB over R squared. So 9 times 10 to the 9th Newton meters squared per coulomb squared. A is 5 microcoulombs, so 5 times 10 to the negative 6. B is negative 5 microcoulombs, so minus 5 times 10 to the negative 6. And this is going to be divided by R squared, which is 4 meters squared. And when you do this math, you should get negative 0.0141 newtons. Okay, and remember the negative means attracting. And then we would do exactly the same thing for KQAQC over R squared. So 9 times 10 to the 9th Newton meters squared per coulomb squared. A is 5 microcoulombs, so 5 to the negative 6. B is 4 times 10 to the negative 6 coulombs. And the distance between them is root 41, which of course you're going to square. And when you do this one, you get 0.00439 newtons. It's positive, which means repelling. And the final one, FQ equals KQBQC. So you do each combo over R squared is equal to 9 times 10 to the 9th Newton meters squared per coulomb squared times negative 5 to the negative 6 times 4 to the negative 6. That really is a negative there. And their distance 5 meters squared. And I wrote down the wrong answer. Oh, no, I didn't. I was okay. So negative 0.0072. For a minute, I thought I'd written the wrong one in the wrong spot. Okay, so we do all 3 of those because the question asks find the net force on A, so we need these 2. And then when we do the net force on B, we're going to need these 2. And we do the net force on C, we're going to need the 2 at C. So if you were only doing the force on one of them, you'd only need those 2 particular forces. But because this question is extreme, we need to do all 3. So first on A. So if I draw A here, what is E doing to A? Well, one's positive, one's negative. The force is positive. No, the force should be negative, excuse me, top one, which means it's attracting. So what's B doing to A? It's pulling it down. So this is going to be 0.0141 newtons. I've dropped the negative now because I've looked after the direction. Okay, it's told me it's attracting, and so we said, oh, so it's going down. And then what is C doing to A? C is repelling. And so along this line, C is pushing A away, up like this. So this is going to be FAC, and it was 0.00439 newtons. So we're going to have to break C up into its X and Y components. So this will be FACX, and this will be FACY. And this angle will be the same. And we can find that angle because we can do inverse tan of 4 over 40, or 4 over 5. So inverse tan of 0.8. And it should be 38.66. 38.66 degrees. Okay? So now when we go to find the components here, FACX should be 0.0439 newtons. And if you look, it's the adjacent side, so cosine of 38.66. So FACX should be, thinking I have it here somewhere, I just can't find it. So what was it? 0.00439 times 38.66 cos. 0.03428. 0.03428 newtons. And that will be left. Okay? And then we do FACY, and it should be, did I lose a 0 there? I did, but I think I typed it in. 0.0439 newtons sine of 38.66. And so we get an FACY of 4. I can't see it, so let me store that. So what was it? 0.00439 times 38.66 sine. So you get 0.00272 newtons, and it's going up. So now that you have these two, now you're going to do sum of the forces on A. Sum of the forces on A in the x direction, there's only one, so it's easy. It's the 0.03428 to the left. The sum of the forces in the y direction, one's going up and one's going down. So our 0.00272 going up minus our 0.0141, I was just making sorry, I had the right number of zeros there, going down. So you're going to end up subtracting them. So this is my x. And so the total in the y, so minus 0.0141. Shoot. Should be, I think I screwed it up. Maybe. Is it 0? I can't see. 0.0436. I can't imagine how that's right. 0.0436. Okay, I'm going to have to try this, even though we're going to run out of time. Minus 0.002742. Yeah, it's not that. I don't know where I got the number I got.